The title of this presentation is Overview and Concluding Remarks. In this final presentation of this series, I'm going to wrap up with just a brief overview and kind of description of what we've been talking about, particularly focusing on the first three presentations of the series, excluding some of the more algorithmic comparisons or remarks that I made in the fourth presentation, namely the previous presentation of the series. And so just as an overview, I thought it would be appropriate to begin with the first overview slide given from the first presentation in this series, which is pretty much discussing the aspects and salient features and notions of quantum information and how that actually comes into play from the work that we are trying to embark upon. And namely, it was discussing an elaboration of a previous work from 2023 that I've submitted somewhere that's been under review for a bit. And then this 2023 work basically to elaborate upon the two-player setting, which again, like I've emphasized in previous series of the presentations of this series, it actually reflects upon many types of symmetries in a game theoretic sense in terms of how players can interact with each other reciprocally through using entanglement and other aspects of quantum information, and also how that relates to the XOR games. And altogether, a lot of these notions, like I've given in the three subcomponents to this second bullet point on the slide, are relating to the fact that we're looking at how the notions of the bias of a game, optimality, whether exact or approximate, and error bounds were formulated, and basically under a mild set of conditions placed on the XOR game, which I've also included in an appendix for some types of alternate versions of error bound inequalities and related types of objects from the action of suitable linear operators, or even like how I described in the second presentation of this series, the information theoretic intertwiners. This allows us to be able to formulate the same set of conditions for the dual XOR, the XOR star games, and even the compiled XOR star games, which is basically another type of variant of the XOR game in which, from a reference that I cite, they provide some closed form expression for the optimal value of a strong parallel repetition of a compiled XOR game, and it pretty much almost fits in very neatly and very succinctly with a lot of the types of arguments that I provided in the main body of the text, the upcoming preprint that I'm going to submit in a couple of hours, and how that actually results to solidifying and pretty much codifying together all of the notions of exact and approximate optimality from quantum strategies, and what would be the expected duality gap between a classical strategy and a quantum strategy. And altogether, as given in the third item, from the perspective of this 2023 work that I gave in terms of the exact and approximately optimal frameworks for XOR star and FFL games, it remains as an open direction of interest, particularly in formulating more generalized error bounds, in addition to other objects that will be introduced in this presentation for games with more than two players. And as such, altogether, with all these considerations in mind, to demonstrate the sources of potential quantum advantage in information processing tasks, we further analyzed and expand upon the three directions that were provided in the previous bullet point, the second bullet point on this slide, in which is just basically establishing some type of correspondence or some type of salvageable notions with regards to information processing that can be further generalized from the CHSH game to the XOR game, and even to multiplayer versions in strong parallel repetition variants of these games. And obviously, also for the FFL setting through the FFL game. And again, I thought that was really helpful to be able to provide one of the boxes or one of the tables that I had given in the first presentation in the series, because that was very much drawing, again, the attention of the viewer to the fact that this quantum, these proposed sources for quantum supremacy, like how have been, experimentally verified for different types of molecules from, say, Google Quantum AI or other industry leaders in quantum computing. It takes upon a more theoretical flavor in these types of collections of results, because it's very much relating to the fact that we're trying to realize or have some type of intuition or grasp of what a proposed advantage or a proposed source of quantum supremacy would be for information processing tasks using these quantum strategies. And again, just to remind the viewer, to reiterate, as I've been discussing in the first presentation of the series, these collection of theorems altogether are pretty much looking at three XOR games through n XOR games for an arbitrary number of players, and it's looking at primal feasible solutions, namely if the viewer recalls in previous presentations of this series, I talked about primal feasible solutions from being able to formulate well-posed semi-definite programs and how there's a partial ordering over the positive semi-definite cone that's actually allowing us to be able to establish that these types of constraint optimization tasks with regards to the partial ordering of the positive semi-definite cone are well constrained, and they can actually be used to accommodate several types of potential dynamics between players when they're responding to different questions that are drawn from the referee's probability distribution. And besides this, obviously, from theorems 1 through 5 that are given from this table, which is appearing within the first couple of pages of the preprint that I'm going to submit soon, is pretty much relating to the fact that we can also look at the existence of primal feasible solutions for either the XOR setting with an arbitrary number of players or multiple number of players, and being able to formulate error bounds and generalized error bounds, and even also looking at the restriction of two-player dynamics to strong parallel repetition of the FFL game. And again, the viewer will remember from previous presentations in this series that I really emphasize a lot of aspects from the perspective of the optimal value of a strong parallel repetition or ordinary parallel repetition of the XOR and the XOR star games, and how that fundamentally differs because the operation of taking strong parallel repetition, it's multiplicative with respect to the maximum winning probability of these games. Whereas for the FFL game, it's invariant, namely the optimal value of two strong rounds of or 2 rounds of strong parallel repetition for the FFL game is exactly equal to the original game before having performed the strong parallel repetition operation. And pretty much, as we've been also talking about the parallel repetition operation in terms of these quantum information processing tasks, it's in looking at, again, like we've been mentioning, proposed sources of quantum advantage for different types of players that Alice and Bob or even an arbitrary number of players can adopt. It's really dependent upon pretty much running different shots or different rounds of any type of game in parallel in determining how you can translate that type of repetition of the game for however many types of rounds you can look at depending upon the circumstance, and how this is actually relating to several types of information theoretic aspects, and in particular very intrinsic notions of quantum information that can definitely absolutely appear counterintuitive, but that's still, when compared to the notions or whatever types of aspects of information like entropy or classical entropy or other very well known or well classified aspects of classical information, they're actually demonstrating how these sources of proposed potential quantum advantage can arise. And again, this was given by the fact that we're looking at this map L, which is a linear bijection, and it's pretty much allowing us to, amongst many properties, such as the ones that are given in the 4 properties from this slide, the fact that when we're in the 2-player setting, we're looking at a linear bijection, namely a linear map between the tensor product of the Hilbert space of C of dA and C of dB, namely the tensor product of the Hilbert space for Alice and Bob. And this is just representing the individual spaces over which these 2 participants and these 2 players in the game can prepare any type of information and hopefully harness and make use of entanglement for various information processing tasks with quantum information. And from the pre-image space that's given from the tensor product of these two Hilbert spaces corresponding to each one of the players, we're mapping into the space of complex value matrices. So namely matrices with dimension d of A and d sub B, which obviously one can very easily imagine that when you're looking at higher dimensional settings, this map would map into a generalization of matrices with tensors whose entries are taken from the complex valued field, which is pretty much fundamentally reflecting upon quantum mechanics and how you're looking at states that can occur with complex valued probabilities. And again, this is given by the fact that from the first bullet point, we're saying that if we fix some state het U, which is belonging to the Hilbert space corresponding to Alice's measurements, in addition to another state ket W, which is belonging and is spanned or belongs to the Hilbert space of Bob's measurements, there exists some U star in Bob's Hilbert space such that the linear transformation applied to the tensor product of the 2 elements in the respective players or the elements of the Hilbert space for these two players is given by, pretty much converting to an outer product from an inner product to an outer product from the tensor product that we're looking at the image of the linear bijection from, in addition to the fact that from the product of a matrix under the image of under a quantum state under L, we're looking at the fact that if you fix some U, which is belonging to Alice's Hilbert space, there exists some A, which is belonging to just a set of matrices with dimension D sub A, which have entries in the complex value field such that A applied to the image of the linear bijection of U is equal to the image of the linear bijection of A tensor product with the identity ket U. And then for the third bullet point, there's a similar type of property that's given in the second bullet point, namely given by the fact that instead we take an element of Bob's Hilbert space instead of an element of Alice's Hilbert space. And then finally, for the fourth property, for this linear bijection, we're having a Frobenius norm inequality, which is given by the fact that if we take some image which is belonging to Bob's Hilbert space, the Frobenius norm of the image of the linear bijection of this element taken from Bob's Hilbert space is just the element itself that we originally fixed from Bob's Hilbert space. So again, this is just really demonstrating how that fundamental properties of quantum information, how we expect the tensor product and the Frobenius norm to behave or to react with respect to this linear bijection is pretty much reflecting several types of characteristics of inner and outer products, which are coming into play when we're constructing more complicated quantum states and more complicated operators from observables from any number of players which are participating in the game. And as we've been mentioning, and that it's very important just to again reiterate, is that namely under the operation of strong parallel repetition, the FFL game is significantly different from even strong parallel repetition of the 2XOR game, from the fact that, again, the omega of FFL wedge FFL, namely two identical copies of strong parallel repetition of the FFL game, is equal to the optimal value of the FFL game itself, which is equal to 2/3. And besides the fact that obviously one can imagine that any types of inequalities or even like we had mentioned, the specific piecewise defined functions that we're using that we talked about in previous presentations of the series for talking about the dual objectives or the dual objective functions from dual semi-definite programs. It's really ultimately relating to this invariance, like I mentioned, or this equality of the optimal value of the FFL game before and after performing strong parallel repetition 2 times. Another classical and quantum values from the literature have been characterized for a wide variety of games, in this case for the torpedo game, which is just given by the fact that other optimal values with such classical values have also been computed, which are dependent upon partitions of the D by D grid, so like either some 2 or 3-dimensional grid. And such values are of the form, namely that for the torpedo game in the 2 by 2 grid, we have a 75% winning probability for using a classical strategy, whereas when we even go to 3 dimensions for the torpedo game, even using a classical strategy, our winning probability can actually increase to 11/12, which is already demonstrating how we can already hope to maybe increase the winning probability, even if we're primarily restricting ourselves to to classical strategies, and how, in fact, as I emphasized in the first presentation of the series, we can look at different types of circumstances under which this quantum supremacy or the benefits or the advantages of making use of quantum solutions for strategies of players in the game, it can become more pronounced as we're either increasing the underlying dimensionality and hence the combinatorial number of strategies that each player can make use of. And the 2XOR bias is given by beta of G subscript S, and subscript S corresponds to the set of all possible strategies that any one of the players can use. And then the 2-player case, it's given by a summation over little s in big S and little t in big T, respectively, which is given by the number of questions that are distributed from the referee's probability distribution to each one of the participants in the game. And it's given by the game matrix, which is indexed in each one of the possible questions, little s and little t, that can be distributed to the 2 participants, as well as a mixed quantum state where you're taking the tensor product of a sub s and b sub t in the intermediate component, and you're forming and you're sandwiching this tensor product operation, this operator from the tensor product, with a mixed state of bra psi and ket psi, as well as given by the fact that you're looking at A sub big S and B sub big T being the union of all one of the questions from that the players can use to respond to questions from the referee's probability distribution, each one of which are given by +1 and -1. So it's corresponding to whether with probability, 0 or 1, each one of the players in response to the questions drawn from the referee's probability distribution makes a correct response, which can constitute a winning strategy for the game for demonstrating some proposed sources of quantum advantage that we would like to further expand upon and further study in multiplayer and higher dimensional settings. And the linear relation between the bias and the optimal value is given by just the following relation, that they're linear related before we're taking that supremum over the script S set for the set of all strategies of the game, or the set of all possible strategies that players can use while they're participating in the game, as well as given by the fact that, again, we can introduce a notion of the bias as well, which is independently of each possible strategy S, which takes the following form, namely, we're looking at the supremum over all possible strategy script S, and when we're taking the supremum and we're making the assumption that each one of the players can make use of and appropriately formulate some notion of what's exactly or approximately optimal for whatever questions they're responding to from the referee's probability distribution, we can maximize over the set of all possible strategies to get some bias beta sub g that's independent of script S, namely the set of all possible strategies for each one of the players in the game. And again, like we've been talking about exact and approximate optimality of biases and how this can reflect to optimal values or the maximum winning probability of a game, as well as error bounds, whether you're looking at second order, third order, generalized notions of error bounds. This is given by the fact that in terms of the bias, the middle term, which is beta sub g sub s, which is the bias that we're looking at or that one can consider before we're taking the supremum over all possible strategy script S, it can be upper bounded from the supremum of the bias independently of each one of the strategies, as well as in the lower bound, a multiplicative factor of 1 minus epsilon for some epsilon taken sufficiently small of beta sub g. So this is just one of the many manifestations and many ways in which epsilon approximality, which is ultimately relating to the bias and the quantum information and the quantum states that one defines for looking at even the bias in the 2 XOR case, it results in it pretty much carries over in a very nice way, and it constitutes a very nice interpretation about the constraints that different players in multiplayer settings would have to take into consideration to be able to have an exact or approximately optimal strategy for hopefully winning a game in the most optimistic case. And the 2 XOR optimal value is recovered from the following supremum over the tensors A and B and the optimal strategy psi, which is given by the fact that this is a type of supremum problem that, again, it's a little bit different from the aspects of the semi-definite programs and the constraint optimization, as well as the constraints with respect to the partial ordering of the positive semi-definite cone, which comes into play for those types of constraint optimization problems. But nevertheless, for this case, it's actually demonstrating how instead we're taking supremum over the strategies, as well as the tensors A sub I and B sub jk, which respectively correspond to tensor representations or even lower dimensional representations if we're just looking at the potential answers that the players, respectively Alice and Bob, can provide to the questions drawn from the referee's probability distribution, and is given by a combinatorial normalization that's scaling with regards to little n sub choose 2, namely the total number of ways to distribute little n questions from the referee's probability distribution to 2 players participating in the game, as well as a summation over 1 less than or equal to I, less than or equal to j, less than or equal to n. And then this is given by the fact that we're looking at, in terms of maximizing over the summation, this mixed quantum state where, again, it's familiar, or it's at least very similar to a previous state that we gave earlier in the presentation, because we're using some bra and ket of some optimal value or some type of strategy that we want to take the supremum over for being able to realize the most quantum advantage in this game that we're participating and we're playing in. But the intermediate part of the superposition, like how I've even been mentioning and describing, it's capturing the probability of each one of these tensors or these possible responses from the players from Alice and Bob to be able to win or lose the game. And pretty much when you look at it this way, in namely the fact that those three terms are corresponding to winning strategies, as well as the minus is actually corresponding to a minus, and a pejorative type of effect on the type of maximum winning probability that we're using to quantify for the 2XOR game given from this optimization. It's pretty much coming into play about the types of conditions and very clearly illustrating what winning and possible losing conditions different players would have to use for being able to succeed at some type of game that they're playing with quantum strategies. And again, in the optimization provided on the previous slide, each broadcat state corresponds to the following product of tensors from each one of the players, namely ket I bra I sub j corresponds to a sub I b sub ij. Ket j or bra I sub j corresponds to aj and bi sub j, as well as in the third item in the line, ket I and bra j sub I corresponds to ket I and b j sub I, as well as the minus term, like which we have mentioned, it has a negative effect in terms of the sources for the potential quantum advantage for being able to win the game and increase the winning probability as much as possible using a quantum strategy is given by the correspondence minus ket j, bra j sub I, and a sub I, or a sub j, b sub ji. Okay, and as we have been mentioning, the strong parallel repetition of the 2XOR game and its optimal value, it's given by the following relation, namely the operation of performing 2 rounds of strong parallel repetition for the 2XOR setting is given by an identical product of 2 copies of the maximum winning probability using a quantum strategy for the XOR game, and given by the fact that this is equal to 1/2, equal to the product of 2 individual factors, and it's not equal to the optimal value of the XOR game itself, which is equal to 1 over square root of 2. So again, it's demonstrating how the original expression, which so many people in quantum information theory talk about in terms of the optimal value for winning the CHSH game, which is cosine squared of pi over 8, that's really even coming into play into the operation of performing strong parallel repetition and demonstrating how certain fundamental aspects about how the quantum information is changed after performing individual shots or individual repetitions of a game are reflected from this different type of relation between the optimal value under strong parallel repetition of the XOR game and the optimal value under strong parallel repetition for the FFL game. And again, what's really important, and that I've also emphasized in different parts of the preprint that's going to be showing up on the archive, is that there are a lot of ways to further generalize also notions of entanglement and how that comes into play from different types of ways that Alice and Bob can be able to muster and be able to, or like manifest, I guess is the right word, or make use of quantum advantage. And that's basically given by the fact that the CHSH of 2 for the n is equal to 2 strategy is comprised of the following Bell states, namely, you're looking at the tensor product of the identity with itself, as well as given by the fact that you're also looking over other tensor products that are taken with respect to these 2 superpositions. And you're basically looking at, namely, in the first equality, the tensor product of the identity with itself, which is applied to some superposition of quantum states, which is pretty much like a lower dimensional counterpart of the GHZ state, which I've drawn the attention of the viewer to in the first or second, and I think even second presentation of the series, as well as given by the fact that the corresponding Bell states are generated by the tensor product of operators, which are either depending upon the sigma x or the sigma z or the sigma x and sigma z simultaneously, which is just basically only having which is just basically only having the effect of interchanging the sign in which certain terms appear, as well as the occurrence of zeros and ones. So it's basically like almost like performing a type of bit flit or interchanging or modifying parts of the Hilbert space that are underlying the overall state in which these 2-player responses live and are defined over. And the SDP formulation was given by the fact that even for the 3XOR game, we can look at a way to define the primal feasible solution for the semi-definite program, which again, it's given by for all z prime, namely the feasible solutions that are given for the semi-definite program between little I between 1 and 3, because we're looking at the 3 XOR setting, there exists some real number, little c sub I, such that a matrix f sub I multiplied by the gain matrix is identically c sub I for I between 1 and 3. And we're maximizing over the supremum of the product of the primal feasible solution with the game matrix for the game, for the 3 XOR game. And under strong parallel repetition, we can have the following SDP formulation, namely where the strong parallel repetition matrix G sub XOR wedge an arbitrary number of times of strong parallel repetition or applications of strong parallel repetition of the XOR game is of this form. So we can just basically distribute the big wedge corresponding to n rounds of strong parallel repetition over individual components of the game matrix to build up or to be able to construct a more complicated object for the game matrix and even higher dimensional analogs of the game matrix with the game tensor. And the SDP duality gap formulation is given by the fact that we can look at the following supremum, which is just given by the fact that we can look at a duality gap, like how I've been mentioning, or just basically a way to be able to formulate some proposed notions of quantum advantage that different players can use by looking at y sub I, f sub I minus the game matrix times the primal feasible solution z prime. And again, in the case of the 3 XOR game, this is reflecting upon the fact that we would expect that there would be a primal feasible solution that could also be optimized over through this constrained optimization scheme through the same partial ordering of the positive semi-definite cone that we're using for defining this semi-definite program for the 3 XOR game. And the positive semi-definiteness conditions are given by the fact that, again, we can look to form a symmetrized version of the game tensor, which is, again, coming into play in that we're just basically making a more complicated representation that's just directly proportional to the game matrix itself. Namely, for the N XOR game, we can look at the symmetrized game tensor by saying that we want to be able to construct a representation of matrices or of tensors, just basically putting along the diagonal zeros and along the anti-diagonal the transpose of the game matrix or the game tensor, and the remaining element of the anti-diagonal, the original game matrix or tensor itself. And this is coming into play because, again, as I've been saying directly on the slide, which is taken from a couple of the conditions that I've defined in this upcoming preprint, besides the symmetrized game tensor that's introduced in the n-player settings, obvious counterparts of the GN XOR symmetrized game tensor are introduced. And such tensors appear in the collection of constraints that are included below, which is, again, ultimately relying upon the partial ordering induced by the positive semi-definite cone. And each one of these individuals' conditions is basically relating the fact that that we're looking to be able to characterize some types of sources of potential quantum advantage from the primal feasible solutions to the semi-definite programs. And this is given by, for instance, in the first case, that the symmetrized game tensor for the 3 XOR game as well as for the N XOR game, any number of multiplayer settings for the N or extensions for the N XOR game, it's given by the fact that with respect to the curly inequalities from the partial ordering from the positive semi-definite cone, we're performing some constraint. Basically, we're performing some optimization procedure pretty much from this constraint, which is entering into the condition for the dual semi-definite program that we're being able to obtain by duality of the semi-definite program that we emphasize in several different parts of the series from just basically the primal feasible solutions that I'd first introduced and reiterated the existence of for the viewer for the 3 XOR game. And so, like we've been saying, under the operation of strong parallel repetition, the duality gap can be formulated with the semi-definite program. And it's, again, given by this form. So this is just really illustrating to us how we can take the strong parallel repetition, the big wedge operation of individual semi-definite programs for being able to characterize some strong parallel repetition variant of primal feasible solutions. And again, in some later parts of the presentations of this series, we talked about how we were able to upper bound a collection of Frobenius norms, which is given by the fact that in the two-player setting, it's comprised of two inequalities in which we're upper bounding a Frobenius norm from the two-player case under the action of a suitable linear operator for the FFL game, in terms of just the Frobenius norm of the suitable linear operator, that suitable FFL linear operator itself. And we had talked about how there can be very specific ways and very salient aspects and different aspects of quantum information as opposed to classical information, which are determining these prefactors of 9 and 44 over 3, which are appearing in each one of the upper bounds. And again, we can form the dual semi-definite programs which have some objective y. And again, we looked at several different types of ways to be able to formulate this y dual objective function, and how that pretty much is ultimately relating to different types of ways that we can enforce conditions over strong parallel repetition of question sets for these players, and how ultimately it's a straightforward extension pretty much of the dual semi-definite programs that can be defined for original games before taking strong parallel repetition. And the FFL upper bound for the Frobenius norm is given by the fact that we're looking at different types of ways to obtain some type of upper bound under the action of a suitable linear operator under strong parallel repetition, which is just given by a straightforward extension that I gave in the previous slide, in which you're looking at replacing the strong wedge, the strong parallel repetition operator, under two operations of strong parallel repetition for the FFL setting, which is allowing us to obtain some type of upper bounds for the Frobenius norms, as was given from similar types of inequalities from the two-player setting before we're performing any strong parallel repetition. And a second example of strong parallel repetition, but for the XOR game, is given by the fact that, again, like how we've been emphasizing, is that there are different types of aspects of strong parallel repetition which are appearing for the XOR games or the FFL games. And this is pretty much given by the fact that you can look to form some strong parallel repetition operation of individual tensors that Alice or Bob or any types of players can apply for games that they're playing using quantum strategies, and how that actually pretty much results in a second type of error bound for an arbitrary number of strong parallel repetition operations for the 2XOR game, which is given by this type of inequality. Namely, the first term is given by some strong parallel repetition operation applied to Alice's tensors, and then the Alice's observables tensor product with identity minus some identity that's also with the tensor product of some other more complicated superposition that I had emphasized in previous presentations. And one result of the error bounds, such as those indicated in the previous slide, is the following relation between the set of players, namely that for epsilon approximality of strong parallel repetition, the viewer will remember that pretty much I had discussed several types of ways to be able to formulate upper bounds for epsilon approximality in the bias, which is very much coming into play from these sets of inequalities, in which we having upper bounds for the G3 XOR game, the GN of XOR game, as well as strong parallel repetition variance for the N XOR game in the FFL game, which is just resulting in the fact that we're taking a summation over some number of terms corresponding to the set of possible questions that each player can provide for the game, and actually providing some upper bound in terms of epsilon approximality of the bias. And under strong parallel repetition, as characterized in several types of game theoretic situations, the action of the suitable linear operator is shown to take the form, namely that we're using script T to denote some type of generalization under strong parallel repetition for, like how we had mentioned in a previous inequality that we reiterated on a previous slide for strong parallel repetition of the FFL game, and how that pretty much results to being able to anti-commute or intertwine, if you would like how it described and provided one interpretation of these types of operators as information theoretic intertwiners for 2 rounds of strong parallel repetition for the FFL game. And one formula for the dual objective Y, which again, the viewer will recall, is related to the fact that we can formulate dual semi-definite programs from this dual objective Y by interchanging the objective of the original semi-definite program as well as the constraints, and also making a supremum in an infimum, and vice versa, making an infimum a supremum, is given by the fact that it's a piecewise defined function given by an optimization from 1 to little n of cubed terms, where 1 to n terms are given by the optimal value of the 3 XOR game, which is multiplied by 1 over a combinatorial factor 3 factorial times n, as well as the previous entries for the piecewise function being defined with also being proportional to omega 3 of XOR, in addition to additional contributions from either n minus one or n minus one times n minus two. So basically, you have this type of cascading product which is appearing in the normalization besides this optimal value for the 3 XOR game, which is also very much contributing to the specific formulation and the specific value of the dual objective, which we're using to formulate the dual semi-definite program. And again, the positive semi-definiteness conditions, like I mentioned from the viewer for the 3 XOR game, all the way up to XOR games with an arbitrary number of players, is given from the partial ordering of the positive semi-definite cone, which is just arguing that this operator itself is positive semi-definite. So namely, that summation over the constraint optimization that I talked about that we're using to enforce the constraint with respect to the partial ordering of the positive semi-definite cone, in addition to subtracting off contributions from the 3 XOR symmetrized game tensor. And again, this is just saying that in a very type of straightforward way, like the viewer will recall in previous presentations of this series, for the 4 XOR game, the 5 XOR game, and the big of n of XOR game, we can define in a piecewise way each one of the entries which are appearing for these functions and for the structure of the dual objective for 4 XOR game, 5 XOR game, and n XOR games. And again, under strong parallel repetition, we're able to formulate a similar type of way as one would expect, namely by looking at whether the optimal value of XOR game or FFL game is invariant under strong parallel repetition or not, namely the fact that the XOR game is not invariant with respect to strong parallel repetition, but the FFL game under 2 rounds of strong parallel repetition is. And the optimal classical or quantum strategies, which again are rooted in describing a lot of the fundamental aspects and fundamental advantages of quantum information that I've been alluding to in this concluding presentation for the viewer, is given by the fact that we're taking a union over players and we're taking a supremum over all possible quantum strategies. Sorry, I changed this in the upcoming preprint, but I forgot to change it on the slide. But these should be quantum strategy script S, because these are quantum states from 3 XOR, 4 XOR, 5 XOR, and n XOR games. And this is ultimately relating upon how these players can hope to make use of entanglement for being able to win the game with a higher, with a higher probability, and more probabilistically speaking, or a higher statistical chance or betting odds of winning a game with some quantum strategy. And again, the error bounds at a glance are given by the fact that we look at error bounds and generalizations of error bounds to multiplayer XOR settings and even strong parallel repetition settings, which is given by the fact that the epsilon approximality factor that I gave for the bias, as well as several other types of inequalities for the player throughout this series, it's given by the fact that it's always appearing in some type of upper bound for the error bounds for 3 XOR, 4 XOR, 5 XOR, and n XOR games. In addition to the fact that we're taking some product over the number of players, like we can see n times n minus 1 times n minus 2, or n times n minus 1 times n minus 2, and n minus 3, and so on, in addition to the combinatorial factor relating to different types of possible sequences that players can interact with questions drawn from the referee's probability distribution for providing their responses. And again, as an overview to close out the presentation, this is just a reproduction, I reproduced basically this slide that was given from the last part of the third presentation, because I think it's a great way to end the presentation and the series out. So just basically saying that to further describe properties of the dual objectives, Y that we introduced from dual semi-definite programs in the previous presentation, namely the second presentation of the series, we continue juxtaposing assumptions that can be placed on different multiplayer games, as well as discussing different piecewise defined functions for the 3 XOR dual objective, as well as being able to generalize that to the dual objectives for many other types of games. And this is helping us establish connections with exact and nearly optimal behaviors for the error bound discussed in the second presentation. And the formulation, again, from the semi-definite program and how that relates to the table of results that I reproduced at the beginning of this presentation of the overview for the theorems for primal feasible solutions to semi-definite programs for multiplayer XOR games, is relating to the fact that we're having different regimes of behavior, different proposed sources of advantage for the strategies that players can adopt, which is indicating us to not only sources of potential quantum advantage, but classical quantum duality gaps. And thanks so much for listening.